All radiation, be it harmful or benign, can be described in terms of oscillating or wave-like electric and magnetic fields in space-time. And if you line up radiation in terms of wavelength from extremely small to extremely large, you have the electromagnetic spectrum, which is shown here. What do I mean by wavelength? Well, before we talk about that, let's talk about wave-like motion. All radiation exhibits a synodial wave, which if you simply put in sine of x into your calculator, will look like this, where you have very high points, which we call crests, and very low points, which we call troughs. The axis of propagation, or the midway point between a crest and a trough, can also be called the equilibrium position. From the equilibrium position to the top of a crest or to the bottom of a trough is known as the amplitude of a wave. The length between two adjacent crests or two adjacent troughs is known as the wavelength, which is symbolized by the Greek letter lambda, which looks like an R but is missing the top half. The point where the wave crosses the line of propagation, or the equilibrium position, is called a node. If you make a wavelength from a line of propagation to the line of propagation in the reverse, a node always occurs at 1/2 the wavelength. It is a point of zero amplitude, meaning that there is no rise, there is no crest. There is no fall, there is no trough. The number of wavelengths, or the number of cycles that pass a certain point in space, is called the frequency, which in physics is symbolized by the letter F, or symbolized by the Greek letter nu, which looks like a V with a little bit of a racing stripe on it. Frequency is measured in hertz, which is cycles per second. And since we have a distance, and we have a per second rating for that distance, you know what's coming next? Velocity. The speed of a wave is equal to the wavelength times its frequency. The electromagnetic radiation you are probably most familiar with is visible light, which has a wavelength between 4 times 10 to the negative 7th, being purple, and 7 times 10 to the negative 7th, being red. Now, here's an interesting question for you. Which light travels the fastest? Purple light, red light, or pick one in between? I hope you're smart enough to realize that is a trick question. All light, hopefully you remember from middle school, that all light travels at the exact same speed. And we have a name for this speed, or at least a constant for it. We call it c. The speed of light is symbolized by the letter c. And c equals 2.9, let's just call it 3. 3 times 10 to the 8th meters per second. So now can you expand on that knowledge? How fast do you think gamma rays travel? You guessed it, 3 times 10 to the 8th meters per second. How about radio waves? 3 times 8 to the negative, or 3 times 10 to the 8th meters per second. All electromagnetic radiation travels at the speed of light. So if velocity is wavelength times frequency, and all electromagnetic radiation has the same speed, the speed of light, when you have a high wavelength, you have a low frequency. When you have a low frequency, you have a high wavelength. They're inversely proportional to one another because they equal a constant. So if the velocities are comparable to one another, or not comparable, or identical between gamma rays and radio waves, why is it that gamma rays give you cancer and kill you while radio waves are flying around you continuously and have no effect on you? there must be something that's making one more dangerous than the other. It's the amount of energy these waves have that makes them more dangerous. So before we talk about energy, well, while we're talking about energy, we have to talk about atoms. In an atom, there is a minimal amount of energy that can be gained or lost by that atom. And all of the energy gained or lost has to be some integer of that minimum amount. Think of it like you have a certain amount of stuff. You can only give it away, like a package. I have a package of the CDs. I have a package deal of CDs. And you can only have one whole package. You can't buy just the Sting CD you want. You have to get the Sting CD with the, Kids Pop. It's the worst package ever. Oh, better example. My fiance likes me for my arms. It's not my awful sense of humor and semi-award-winning personality. She likes my arms. But she can't cut them off and have the same effect. I'm a package deal, baby. And she's got to take all of me or none of me. I'm a quantitized event. And now I've let you in on the personal details of my life. Let's get back to chemistry. The amount of energy that can be gained or lost is equal to that quanta, that integer, which we symbolize by n, times the quantum, which is h times the frequency. What is h? H is Planck's constant, which equals 6.62 times 10 to the negative 31st joules per second. And this formula applies to all phenomena on the atomic and molecular level. Now, I'm assuming you all know this guy, or if you don't, you can figure it out pretty quickly. This is Einstein. And Einstein said that all electromagnetic radiation was quantized. Him and Planck, he liked Planck's work a lot. He said that you could view electromagnetic radiation as a stream of particles, and he called these particles photons, which are massless particles of light. Einstein also gave us the basis for solar power when he theorized about the photoelectric effect, which is the fact that if you bombard a metal surface with photons or light, it causes the metal to eject electrons. And if you increase the intensity of that light, it will increase the rate of ejection. And since we have electrons that are being ejected, they can be accepted by something, thus completing a current. And that's how we have the basis for solar power. He said that photons would emit energy as well, since we know that energy is equals to Planck's constant times its frequency. Einstein was a fan of Planck, and therefore he based his research on that. We can expand that formula even further, since we know that frequency is related to wavelength and velocity, where velocity equals the wavelength times the frequency. And all electromagnetic radiation travels at the speed of light, so velocity is simply c. We can substitute c divided by the wavelength into that equation. So energy equals Planck's constant times the speed of light divided by wavelength. So this is a typo here, but you probably know Einstein for his theory of relativity, where energy equals mass times the speed of light squared. So does that mean then that photons have a mass? Well, if we rearrange this to solve for mass, we have that mass equals energy divided by the speed of light squared. Since we know that energy is Planck's constant times the speed of light divided by wavelength, If we substitute that formula in for energy, we have Planck's constant times the speed of light divided by the speed of light squared times wavelength. 1c gets canceled out by one of the c's below, so we are left with mass equals Planck's constant divided by the speed of light times its wavelength. So yes, it is true that photons do have a mass. In fact, in 1922, a physicist collided X-rays and electrons and showed that photons exhibit the mass exactly as calculated by this equation proposed by Einstein years before. So light can be seen as both a wave phenomenon because it exhibits wave-like properties with amplitude, frequency, and wavelength, but it can also be seen as a stream of photons. So energy is quantized, meaning you have to accept the whole package, and it occurs in discrete units, which we call quanta. Electromagnetic radiation exhibits both wave-like and particle properties, and because it exhibits both of these natures, we call it the dual nature of light. And since light can be seen as both either light or matter, we can rearrange it to solve for the wavelength of something that has a mass, where it would simply be Planck's constant divided by the speed of light and multiplied by its mass. If we knew that an object was not traveling at the speed of light, we could simply substitute v in for c into this equation, giving us mass times velocity, which is your momentum term for those of you who are feeling physics inclined. So the more massive an object, the smaller its associated wavelength. And the smaller an object, the greater its wavelength. So all matter can be shown to exhibit both particulate and wave-like properties. Thus, energy and matter are related to each other. And it's the great cycle of science.